Probability is often seen as one of the least mathematical of the mathematical disciplines. It's the most concrete idea, more or less based on what we as humans expect will happen. It isn't based on some abstract idea like algebra or calculus. The definition for such a seemingly simple idea, however, isn't clear-cut. Throughout history, a total of 4 interpretations of probability theory have been developed: the classical, frequentist, subjective, and axiomatic perspectives. Created by Jacob Bernoulli and Pierre-Simon Laplace, the classical interpretation of probability was the first attempt to provide some rigor to the field. It states that in situations where all the possible events are equally likely, the probability of each should be shared equally. In other words, the probability of an event is the ratio of the number of cases favorable to it to the number of all cases possible, when nothing leads us to expect that any one of these cases should occur more than any other, which renders them for us equally possible. This comes about, basically, from the principle of indifference. Without any relevant information, we should distribute the degrees of belief equally among all the possible outcomes. Mathematically, if an experiment results in n equally likely events, where n sub a of these result in outcome A, then we say P of A, or the probability of A occurring, is equal to n sub A over n. This is the interpretation that describes fair dice and fair coins, but its critics object it can't handle weighted dice, where the actual likelihood may be unknown. Further, it can only handle a finite number of outcomes. The frequentists or empiricists, on the other hand, define probability as the relative frequency over time, or after repeating a process a large number of times, counting how often an event occurs. This is similar to the classical definition in that it defines probability as the ratio or proportion of events, although it enables the mathematician to find the probability of weighted phenomena. If we denote once again, n sub a is the number of occurrences of a in n triangles, and if the limit as n goes to positive infinity of n sub a over n equals p, then we can say that p of a, the probability of a occurring, is equal to p. This definition also faces several problems of its own. It involves performing an infinity of repetitions of a random experiment, where only a finite number of repetitions are possible. And if these are performed and are used to define the probability, then due to the random nature of the experiment, we find it to differ slightly every time. Similarly, it faces the issue when trying to define what a random event is, and random from which distribution of events. Next come the subjectivists or Bayesians, who say that probability is rather the subjective measure of belief in the occurrence of an event based purely on reasonable expectations. As such, subjective probability tends to be called credence rather than chance, which suggests objectivity. This is more or less a fair view on probability, though. For one, it results in different perceived probabilities between people with different degrees of information, and two, it still demands consistency in perceived probabilities. For example, that they cannot exceed 100%. The fundamental idea behind Bayesian probability is that new information shouldn't determine, as if in a vacuum, subjective beliefs, but should rather update it based also on prior beliefs. This is outlined in Bayes' theorem, which states, simply enough, that the probability of a hypothesis given some evidence is equal to the probability of said hypothesis times the probability of said evidence given the hypothesis divided by the probability of the evidence. Finally is the axiomatic perspective, which attempts to unify the 3 definitions above with the coherence or consistency conditions demanded by the subjectivists. As such, it says that the probability is any function p which inputs events and outputs numbers satisfying 3 conditions or axioms. First, that for every allowable event, e, the probability of e is in between 0 and 1. Second, that a certain event has the probability of 1. This is, for example, the probability that sum of all the possible outcomes occurs. And number 3, that the probability of the union of mutually exclusive events is the sum of the probabilities of the individual events, where mutually exclusive implies that they cannot occur simultaneously, and that the union of the events is that at least one of the events occurs. The flaws outlined of the first three interpretations and the low-reaching nature of the fourth are once again illustrated in the two problems covered in my previous two videos. Bertrand's paradox, which as a reminder asks for the probability that a random chord within a circle will be longer than the side length of an inscribed triangle, which as it turned out led to three or in fact an infinite number of solutions. This runs into problems with all three definitions. First, the classical perspective allows only a finite number of possible events, whereas this is continuous and therefore infinite. While this is solved by the frequentist definition, as I discussed, finding a distribution of all possible chords to pick randomly from became difficult and more or less ambiguous. Further, the Bayesian method is similarly ambiguous, as it depends more on belief. Now, the Monty problem is less ambiguous from the perspective of a rational analysis of the classical and frequentist definitions. The chance of winning the car after a switch is certainly 2/3. But as mentioned, this is only in the very idealized, perfectly mathematical scenario of the host always allowing a switch. In actuality, if you were there in the game show, you would have to depend on your beliefs of the host's tendencies, which is an apt scenario chiefly for the Bayesians. The tendency for probability theory's divergent interpretations seems to have been foreshadowed by its conception. Famously, Blaise Pascal serves as the founder of probability as a mathematical discipline as a result of an argument between him and Chevalier de Marais. He argued against the Chevalier's insistence on the danger of applying mathematics to reality and attempted to solve his problems of chance using pure mathematics. This inspired a great part of the field, and after 3.5 centuries we have this mess, which is also the most useful tool we have for determining truth, chance, and credence in this real world. Thanks for watching and tune in for next time.